Okay, can I start? Are we ready? Yeah. Okay, so we're going to do a bit of a reminder from where we were last time and then go on with the new stuff. Last time we talked about generic maps to the plane, we talked about surf paths, and we also talked about surf graphics. And there is one crucial, I guess there's some crucial notions that some concepts that I'd like us to remember. So if you give me a surf path, I can think of it as a level preserving map from r cross n to r cross r. What the surf graphic consists of is the collection of all critical values in r cross r. There is basically three things that can happen locally, which cover all the cases we will worry about. One thing that can happen is that we have a fold curve. So that's something that would be given by a function that can be put into quadratic form. The other thing that can happen is that we may have a CAS, which is something that can happen if we have a family that locally looks like the one I'm showing here in dimension 1, and then we can always add an extra quadratic form if we are in higher dimensions. And the last thing that can happen is that we might have a crossing. So I'm trying to indicate here a one-parameter path of Morse functions, which are excellent Morse in all times apart from the middle time when we have two critical points at the same critical value. One thing that, and then the corresponding surf graphic would basically look like that, because we have what initially was the red critical point, which was above the blue, now has changed relative positions. And at some point, we have them be at the same critical level. One thing that I did want to say, which I don't remember if I clarified it last time or not, this is a nice picture to sort of indicate what's going on. It's a slightly misleading picture because it might lead you to believe that what we actually have is a parameter path of manifolds with different manifolds with Morse functions. That's not how I want to think about it. What we actually have is a set manifold in the background. It's like the sphere minus 4 disks, and we have identifications of it with each of these pictures, and then what these pictures indicate is what the height function will look like. So we have a fixed manifold on the background, and then a family of Morse functions that we get by some predetermined identifications composed with the height functions indicated by the picture. That's what's happening. Is that clear or more confusing? Okay. And I just want to have that as a slogan, that surf graphics are very important tools in surf theory because they allow us to visualize surf paths and also, what will be very crucial for our purposes, interpret homotopies between surf paths as moves between surf graphics. We're going to make this translation. Basically, the goal of the day is to make this translation happen. Sorry about that. Okay, hopefully we're all on board. Okay, and that was just a small reminder from last time. Are we on board? Okay, so if we go reminder way before, so the first lecture introduced the pseudo-isotopy problem, and we reduced it to the following question: if you give me two functions from m cross I to r, two real value functions m cross I without any critical points, and if you give me any path gamma of smooth real valued functions that connects those two f0 and f1, is this gamma going to be homotopic real boundary to a path of smooth functions without any critical points? That's the underlying question. So in a diagrammatic sketch, if you prefer, if this green thing is my space of all smooth real valued functions on m cross I, and if epsilon of m cross I is a subspace of those have no critical points, the question is, am I in a situation like the one indicated on the left, where if you give me any path on f, if you give me any path, I can homotop it to a path that lives entirely within the subspace of functions without critical points, or am I in a situation like the one indicated on the right where this is impossible? That's what we are trying to determine. And I can translate this problem into the language of Cerf graphics. So a Cerf graphic that represents a Cerf path, but with smooth functions without critical points, must roughly look something like that. I have no critical points on the left. I have no critical points on the right. I may have critical points in the middle, which means that at some point I must have introduced some critical points with birth moves. And then at some point I must have killed all critical points with death moves. And I might have some arbitrary complicated things happening here. I might have extra birth deaths. I might have crossings. I have all sorts of stuff. So if you give me a Cerf path between smooth functions without critical points, I would expect a Cerf graphic of that to be something of that sort. Okay.
The two vertical lines are not meaning.
They are. I always, so now I'm drawing a Cerf graph. I usually always put it in a box. But yeah, I mean, I guess that the reason why I'm doing it as a box is that I'm just like you have Cerf graphics, you can also think of Morse graphics, right? You can just have like the critical values on the real line of the Morse function. And that would be, I want to think of this as the Morse graphic of F0, and I want to think of this as the Morse graphic of F1. I mean, that's roughly the, but yeah, they don't play any crucial role. Sorry, I forgot to charge my Apple Pencil. So we can take we can take 30. Yeah, it's okay. It takes 30 seconds to go to 60%, so we can entertain ourselves for 30 seconds. But is that? And actually, I don't need the Apple Pencil for the next 30 seconds. So our task is to prove pseudo-isotopy theorem would be to show that any Cerf path with a Cerf graph like this must be like homotopic real boundary to a Cerf graph to a Cerf path with empty Cerf graphic. That's because that's if you give me a Cerf path without any critical points throughout, then develop the Cerf graph at the end. So that's what we are trying to do. And in order to do that, that's going to be the point of today. What we need to understand. So far, what have we understood? We've understood what generic smooth maps to the real line look like. These are the Morse functions. We've understood what generic homotopies between them look like. These are the Cerf paths. And we now need to understand what generic homotopies between those must look like. This is what I'll be calling two-parameter Cerf paths, not standard terminology, but the one we'll be using. So we need to understand what those are, and it's going to be a very similar process like what we've done so far. We will explain what those look locally like, and the next step will be to translate their local behavior into what it indicates for the relative Cerf graphics. So we'll translate these two-parameter Cerf paths into moves between Cerf graphics. And the first thing that we need to understand to be able to do that is this codimension 2 strata of the space of all smooth real valued functions on a manifold W. So we understood the codimension 0 strata and we understood the codimension 1 strata. And now it's time to go to codimension 2, which would be the last thing that we'll worry about. That's basically a recap of where we were and where we're heading. Are there any questions, comments, or concerns about it?
How about you, Ken?
I think we're good. Okay. So I will first start by telling you. So I want to basically make a list of what the codimension 2 strata of the space of all smooth real valued functions on W look like. And I'm going to start from some very, well, hopefully easy ones, and then gradually we'll get some more complicated ones. The first thing that I'd like to separate this codimension 2 strata in is like two big families, one that I'm calling trivial and another it's going to be non-trivial. And the way I'm going to explain, or the way I'm going to describe all of this codimension 2 strata is that first I'm going to show you a picture which is just more as a form of analogy. It's going to be a picture of how this strata like sits within the space of smooth real valued functions. And then we'll try to unpack this picture and understand it more. So the first case, the case of trivial codimension 2 strata, is basically when we have an intersection. This is a little bit misleading, but it's basically when we have an intersection of two codimension 1 strata. And you'll see in a second why, but I will be calling this kind coincidence strata. So the way those would sit in f of w is I would have some connected components of f0, which in 0 strata, these are the excellent Morse functions, and then I would have a component of f1. This could be either f1 alpha or f1 beta. So this could either have cusps or crossings, and I would have another connected component. So this could be another thing that with cusps and crossings. So if you give me 2 points in f of w, and let's take those points to be here, I can write down 2 paths around this codimension 0 stratum. One would be gamma 0, maybe the other would be gamma 1. Let's try to understand what this looks like in an example. Let's suppose that f0 is this connected component that consists of excellent Morse functions with 4 critical points. So I start with 4 critical points. Sorry. Maybe let's call them C0, C1, C2, C3, C4. And okay, I'm going to describe Cerf graphic for gamma 0. So let's suppose that maybe this vertical line is going to be death of C1 and C2.
Sorry, where did you get the 4 critical points from?
I'm just doing an example. So they're not, I'm just saying. Yeah, so I'm just saying, let's suppose that this particular region, the top left corner, let's suppose that it's a region which consists of excellent Morse functions with 4 critical points. And I'm supposing that to go from this region to this region, I'm crossing this F1 singularity, which is death of C1 and C2. So what would the Cerf graphic look like up to say this point? It would be this death of C1 and C2. And then I would have nothing happening to C3 and C4. And then let me suppose that when I'm crossing this horizontal line, I have a crossing of C3 and C4. So I have something that would look like that. And that would be a Cerf graphic that would describe gamma 0. Okay. And then a Cerf graphic that would describe gamma 1. Again, I start with those 4 critical points, C1, C2, C3, C4. Now I first cross the horizontal line, so I'm first going to cross C3 and C4. And then I'm going to kill C1 and C2. Okay. So that would be the Cerf graphic for gamma 1. And all I'm saying is that these should be two equivalent things. I have two codimension 1 phenomena that are happening completely disjointly from each other, and it doesn't matter at which order they occur. And I have like sort of an evident homotopy between them. Maybe I'll denote it like that, which is going from gamma 0 to gamma 1. And these are what I'll be calling coincidence two-parameter paths. And I'm just calling those coincidence two strata because, so what's happening in the middle? In the middle, I just have a Cerf path. Sorry, I have something that fails to be a Cerf path for an almost stupid reason, because I have a point where I have a function which has both a cusp and a crossing at the same time. And just two disjoint from each other codimension 1 phenomena that by coincidence are happening at the same time. Hence the name. I take blame for it, but that's what this particular type of codimension 2 strata is like. And yeah, is it clear? This is if you go to Cerf, these are like all the cases that basically would occur. I might have like interchanged order in which crossings occur, or I might have first a cusp crossing and then I change the order. And the only thing that would be worth saying is that if I have cusps, and the first cusp, then the second cusp, I can change the order in two ways. I can put one of them below the other, or I guess the other way around. So I have like these two ways in which I can change the order in which the cusps are occurring. Okay, so hopefully there isn't anything counterintuitive going on here. Now we're going to the non-trivial codimension 2 strata. And for some reason, it doesn't update. Okay, let me exit and re-enter. Sorry. Okay, hopefully you can see. So now we go to the big. So what does the big look like? That's the so I'm saying, so the non-trivial codimension strata, I will again separate them into two categories. One is this codimension 2 strata that come from jet constellations. It doesn't matter what that means, but basically it means that if you so the way you get all of this is the same way we did with force functions of the cusp. You use some sort of Thom's jet transversality theorem. And some of the strata you get from using the multi-jet transversality theorem, some of the strata you get from the single jet transversality theorem. So this is what I mean here for multi-jet considerations. So you give me the peak. This is how the big strata sit inside of W. I have one codimension 1 stratum here, which is a cusp stratum, and then I have two other ones which are crossings. And again, if I want to think of what two Cerf paths on W around a big stratum look like, maybe these are like 2 points, and that would be one path between them, and then that would be another path between them. So again, if you'd like to see what gamma 0 looks like, you would have a situation where this here is, let's say this is a birth from first
I'm not. Maybe just
I'm
Yes.
Just slightly I would be nice if I could make precise what that picture type means in terms of the how do I know situation like you,
Which picture are you saying? This one?
yeah, that one. So like given that I'm at the intersection, so given that I'm in the dimension two strata point, like how do I determine which these ones are that?
You would have to do, I think, if I understand the question right, is that you have to do what we're basically doing here. You have to like look at a circle around it,
I see.
and then trace. Yeah, I think that's the only way I would think of answering this. So let's maybe start with this path here. One. What would that look like? Let's suppose that here I have 3 critical points. And let's suppose that this here crosses 2 of them. And then let's suppose that this here crosses the other 2. Sorry. And then let's suppose that I have my clasp. Okay, that's horrible drawing, but that's like the Cerf graphic gamma 1, or would be the Cerf graphic for gamma 0. I would have my clasp, and then I would have the fold. So here I only cross 4-dimension 1 stratas. And there is this intermediate stage where I have something that takes this form. It's basically within my 9th point, I have a CASP critical point, and I have a non-degenerate Morse critical point at the same critical point. This is what's happening here. And it's called a peak, because I guess that looks like a peak. But this is standard.
Yeah. Okay, so that's very elegant. So then my immediate question is just to like when to know whether there can be construction to come to this. In the previous situation, we should have convinced ourselves that we could always find a smooth family of functions that could go from one to the other. But is there, we'd like to be able to make sure that there are structures that
and there are so I mean, if I give you a graphic like this, you can't. I mean, this is something that we will discuss a little bit later on. But you basically need to make sure that this cast and this field are happening independently of each other in the manifold. And we can make like I'll pose a criterion later on. I think it's a very similar question to if you give me a Morse function with 2 critical points, right? Can I always cancel those critical points? Can I always cross these critical points with each other? The answer is no. There are some criteria that you need to have in order for that to happen. And I think it's a very similar thing. So yeah. Yeah, basically, I think what you want maybe to give you an answer as a prelude is that if you look at a critical point here and you look at an ascending disk of it, shouldn't cross any of the critical points here. That's the condition.
can that be made into statements?
I believe, yeah.
Okay.
I believe so.
Yeah.
Okay, I'll be relatively happy with the peak. And
why does it look like where's the peak? Okay.
I think maybe my drawing skills aren't good, but I think with a little bit of imagination, that should at least be reminiscent of a big. Yeah. That's one that I don't take any responsibility for. Yeah.
What did you say what happened on that big path?
What path?
This one was gamma 1.
Yeah.
So gamma 1. And what was something?
Yeah. So I'm thinking of a homotopy from gamma 1 to gamma 0. And this homotopy will at some point necessarily have to cross the pink point. And this is just an intermediate graphic. So you won't be a surf path when you cross that pink point, because you have this phenomenon here, which I exclude from surf graphs. But you can still write down a graphic, and that's what it's going to look like. So maybe I'll use a different color to indicate. It's like a path like this, which is going to be intermediate.
And we can have the scenario on the first class. The two biggest.
Yeah. Yeah. So you would have, I didn't draw it, but you would have, right? So you would have a path like that, and the surf graphic for it would look like that. Yeah. I don't know if I did right, but yeah, roughly this should be. Yeah, again, modulo my drawing. Yeah. Yeah, exactly. I actually like this terminology. It's not bad, right? Yeah. And okay, so we have a coincidence on the beak. Let's do triple point. So in the triple point, you have a situation which will look like that in f of w. We're going to have 3, 4. So these are all f1 betas. So these are all crossing one strata. And if you consider 2 surf paths, so here I'm considering those 2 surf paths, let's think of what the surf graphics are going to look like. We are going, yeah.
Because they're all F1 beta, they're all crossings.
They're all crossings.
Yeah.
Exactly. Okay. Exactly. Yeah. And so what is this going to look like? Let's see. Let's suppose that here I have, let's suppose that here I have a connect component of F0 with 3 critical points. So I'm writing 1, 2, 3, C0, C1, C2. And let me suppose that this line is, I don't know, a C0, C1 crossing. So I'm going to call it 0, 1. And then let me suppose that this line is 0, 2 crossing. So I'm going to have something like this.
Number 1 now, right?
I'm drawing gamma 1, exactly, yeah. And then the last one will be 1, 2 crossing. So I have 1, 2, and I cross them together. Right, that's what gamma 1 would look like. So what is gamma 0? Let's see, again, we have 3 critical points, C0, C1, C2. First, I have this crossing. Remember, this was a 1, 2 crossing. So I'm crossing 1 and 2 together. Then I have a 0, 2 crossing. So I'm crossing those 2 together. And then in the end, I have a 0, 1 crossing. So that was my 0, and that was my 1. So I have to cross those 2 together. Okay, so basically this codimension to strata gives rise to a move between Surf graphics of this form, which is just the randomized theory. This is a randomized theory move. And like the intermediate, if I were to draw like this intermediate path, it would basically be something like this. So I would have a triple crossing.
And again, you can write this down to only
yeah, exactly. So there is, yeah, so you can write it in terms of different statements in terms of the surgery spheres, and then what Surf does is you can then take a next step and determine when this statement will be true for like, yeah, it's basically you say that, you know, under any conditions in any dimension, I can have such a crossing if and only if something happens.
Yeah.
And then there is a second step, which is this will always happen if the dimension is big enough and you have no I1.
And just to be clear, like we arrived at these various classes by looking at the transversality theorem.
Yeah.
Okay.
Exactly. Which,
for example, there couldn't be a coincidence of 4 lines. Doesn't take place.
no.
It's not the right dimensions.
No, exactly. Because if you have a coincidence of 4 lines, you can always push one. For the same reason that in one parameter paths, you didn't have a coincidence of 3 lines. You could always push one. These you can actually see it from here, right? Like you can always avoid this blue line by pushing it up or down, but you can't avoid it in a 2-parameter family. That's the, yeah, but exactly. Okay, now are we ready for the, so these were the codimension 2 strata from multi-jets, and now we can go to the codimension 2 strata from single jet considerations, which there's only one of them. It's very beautiful. It's a swallowtail. Are we ready for it, or questions about? I don't want to. Yeah, please.
Why are we calling them codimension 2?
That's because, now it's a good question. So remember we were having f of w, which is the space of smooth real value functions. And then what I'm saying is that, you know, this space is very big, very complicated. I want to look into pieces of it which are a little bit more manageable to understand. So we have this stratification, or like I'm trying to construct a stratification of it. And so when you have like a stratified space, like F0, where was the codimension 0, like stratified part of it. F1 was the codimension 1 stratified part of it, and F2 was the codimension 2, and will be the codimension 2 stride part of it. You can think of that in 2 ways. One, you can, yes, yeah. You can think, so one way you can think of it is, so the space of smooth real value functions, it can be made into some kind of infinite dimensional smooth manifold. And these F0, F1, F2s are literally co-dimension K submanifolds of it.
Obviously, in our drawings here, we're limited up to codimension 2 because we're drawing it as a point already.
Yeah.
Okay, but we could go arbitrarily.
We could, yeah, of course. Okay. Yeah. But
sorry, tell me, Filippos.
Yeah.
What would happen if you had more than 3 F1 beta strata crossing at a point, or can't that happen? Maybe this is related to what Bruce was asking.
Yeah, no, it can. Right. Well, if you had, I mean, again, you have to take these pictures with a little bit of grain of salt, because they're like 2-dimensional analogs of a very high-dimensional thing. But in terms of the analogy, that we are trying to build, what would actually happen would be something of this sort. Yeah, so if I am in this situation, I can always push this guy, like I can always turn it into something like this. So it wouldn't be something like that would generically occur.
That argument makes sense, but then sort of like you think, well, you could do that with the other line as well.
Which other line?
That middle one, couldn't you? Like you could just move that away. Get rid of the triple point completely.
That's right. Yeah, yeah, that's right. This argument is not good.
It's a good argument, but something needs to be added to it.
Yeah. And what needs to be added to it? Yeah, I mean the problem is if you let's actually see it. Yeah, let's suppose that I had to do this thing instead. Okay. And let's suppose that I had four crossings now. What would the relevant Cerf graphics look like? Let's see if I can do this. I would end up well. I'm just gonna show this picture, I guess. Let's see. I'm not sure if this is gonna work, but yeah, I think the argument is that this can always be avoided in two parameter families, but you wouldn't be able to avoid such a situation in a 3-parameter family. I'm not giving. Let me. Yeah.
You'll give us a better explanation tomorrow.
I might. Yeah.
Okay.
But it's this sort of basically it's this sort of argument that you would have to make to see this. Okay. Are there any more questions, comments, or concerns for triple points?
Make sure Ken's okay.
All good on your side, Ken? Brian, are you still with us?
I'm with you, but I'm having difficulty with my connection.
Okay. Okay.
Okay.
Cool. Thank you.
Okay. There is a little R here, which I have no idea where it comes from, but well, we'll see if this is going to be a problem later on. Okay. Okay. So are we feeling ready for the swallowtail?
Yeah.
So in the swallowtail, this is roughly what the configuration would look like in f of w. We would have two CASP codimension 1 strata at this point, and we would have a crossing codimension 1 strata, and would all meet in this codimension 2 stratum, which I'm calling the swallowtail. And again, we will have two paths that I'm drawing here, this gamma 0 going around this side of the swallowtail, and then this gamma 1. So I wrote some other things which I want to skip for a second, and I want to show you the Cerf graphics. Oops, sorry. Okay, So let's suppose that I start here with a single critical point. And then here I have a birth. So I'm going into 3 critical points. So this would look like that. Then I have a crossing. So this is going to look like that. And then when I cross here, I have death. So this is going to look like that. And this is roughly what the SERF graphic, well, a very bad drawing of the SERF graphic for this gamma 0 path. And then for the gamma 1 path, the SERF graphic is just this line. And this is, so I guess this is meant to look a bit like a swallowtail, which is why this is called a swallowtail. Again, drawings are quite bad. And so the idea is that if you give me a SERF graphic like this, under some conditions, I can delete this part and simplify it to a self graphic with only folds. So this gives us a way to cancel 2 cusps and a crossing together. And so one way that this can happen is if we have a 2-parameter path. So first of all, I should say the swallowtail is actually a genuine singularity, just like we have the cusp, which is a genuine singularity. The swallowtail is a genuine singularity, and it's a singularity that if you had takes this canonical form. So so the function around it, takes this canonical form. It's a quadratic plus minus an xn to the 4, and the plus minus has to do with how I am drawing this picture. I chose to make the birth happen above this fault line. I could have chosen it to happen below it, and that would give us a plus or a minus. And a 2-parameter path will be a swallowtail 2-parameter path if locally it takes this form that I have here in the green box. So it's some kind of quadratic. It's a 2-parameter path, so it has 2 parameters s and t, some kind of quadratic, and then this part here, which belongs on s and t. And when s and t is 0, I get a local form around the swallowtail singularity. So at least that's the idea. I'm going to give you a demo, but do you have a question? I mean, if you haven't seen this before, it's a little bit hard to digest. But
when you say this one, there's an actual singularity. What does that mean precisely?
So in all the previous codimension 2 strata that we've seen, what's basically happening is that you have 2 things which are like the previous 2 strata that we've seen don't come from a singularity of a function. They come from like 2 codimension 1 strata that somehow interact with each other in a non-generic way. Like when we had 3 critical points of the same critical value around, like locally around any of these critical points, there isn't anything that locally would make you say that, oh, we are in a codimension 2 stratum here. Like around each of these critical points, locally everything is very standard. And being in a codimension 2 stratum is something that we can only see from global behavior. The swallowtail, and this is why, and this is related to calling these as coming from multi-jet considerations. That's where the multi-jets are needed for. But for the swallowtail, this is different. The swallowtail itself is an actual singularity, like the local behavior of the function around it is different than the local behavior of the function around the cusp or the local behavior of the function around the Morse critical point. And
So like in the local chart, it looks like,
So in the local chart, it looks exactly like this.
yeah, because like with our non-degenerate critical points in the local chart, they got up to quadratic.
Exactly.
For both depth when they got up to cubic.
Exactly.
So now we have a higher.
Exactly.
Okay.
Exactly.
Yeah.
And exactly. And then you have a two parameter path that crosses a swallowtail singularity will generically look like this one. So remember, it's the same thing what happened when we introduced CASP critical points and then we introduced birth-death paths. So birth-death paths were like surf paths that crossed CASP critical points in a generic way. Similar thing that's happening here. We introduce CASP singularities, and then we introduce two parameter paths that cross a CASP singularity in a generic way, and those are the swallowtail paths.
And just to remind me, here's a little gap, not a gap, but I mean something that Cerf doesn't need for his paper. Like he doesn't need to show that every two parameter family is actually equivalent to one of these, or something like this.
Yeah. So that's true. So Cerf actually, yeah, and it's a little bit. There are some places in the literature where you can definitely see the claims that these two parameter paths are stable and generic within the space of all two parameter paths, but you'd find very hard to find the proof of that in the literature. But Cerf didn't need it. And you'll see the sort of arguments in a bit. You'll see the sort of arguments in which those show up, and you'll see why he didn't need it. But I did want to show. I mean, you've seen this demo before, but I
want to see it.
You want to see it again? Okay. So try to keep this picture in your mind if possible, and we'll come back to it. But okay. No. Okay.
It's not over yet.
No, it's no. I didn't save it. Damn. Okay. I can do it. I can do it very quickly. But sorry about this. Minus s x squared.
In the meantime, I'm gonna get Lisa to take a picture.
Minus tf. Okay, it's I'm actually I think.
Making progress.
Yeah, I'm actually ready. Ready for it. It's fine.
You're so fast.
You can tell him on
Yeah, I've done this many times, so.
on the click.
But then you guys won't be the same because he won't be giving explaining.
Okay, so now we ran into this other problem where the picture on my iPad doesn't reflect the picture that you're seeing. It's okay. I'll stop and reshare. What is live without some technical difficulties? Okay, perfect. So I just want to give you a demo of what the swallowtail looks like just in dimension 1. So I have this map from R to R. It's a two parameter family of maps. The two parameters are S and T, and the formula is x to the 4th minus sx squared minus tx. Okay, that's a two parameter family of maps from R to R. And I'm just going to fix S to something positive, and I'm going to vary T. So if I start with, I don't know, if I start with like T being very negative, I have a map with a single critical point. I guess here you see the critical value of it, and then in the graph there's no other critical points occurring. Okay, and now if I start varying T, maybe I should not have made it. Okay, you'll see there's going to be a time when in the right part of this graph, you'll see a you'll see a birth and then two critical points emerging. See that? And now these two critical points will come together. They'll have the same critical value around here. They'll cross exactly. And then now you'll see the other two, which are about to die. And here they died. Okay. So this was just showing basically what you were seeing. Bruce very excited. Yeah, it's basically showing in like with like a demo what you're seeing, like an example of a two-parameter. Sorry, I guess here a one-parameter path because we fixed S that has this Cerf graphic. We started with a single critical point. We had a birth, we had a crossing, we had a death, and then we ended with a single critical point. And now that's for like positive S. If I make a negative S, what you will see is that, and I vary my T from something that's negative to something that's positive, you'll see that I just have a single critical point throughout. There's nothing happening. So that's the Cerf graphic for this path would be this Cerf graphic. And then, because this is a demo that gives you everything, if you put S equals 0, okay, and you start with a negative T, now when T becomes 0, yeah, exactly. So you have this like the swallowtail is in the...
So that's as you're pinching the swallowtail side.
Exactly, precisely. And yeah, and that's well, that was the demo, but hopefully it makes it a little bit more like familiar about what these things look like in practice. And now this isn't, I just, you're not going to see this anywhere. I'm a little bit motivated from Chris Schomer-Priest's thesis here, but I just want to like concentrate everything that we've seen so far in the course in like one like organizational gadget. So I'm calling those stratification trees, and we defined 3 strata. We've defined so far the codimension 0 strata F0, which is the strata of excellent Morse functions. We defined F1. F1 has 2, it's like codimension 1 strata, and it has 2 types. There is one type that we get from multi-jet considerations, and this is the crossing. And then there is a second type which we get from single jet considerations, and it's the CASP. Okay. And then 3 for F2 would look something like that. We have a trivial codimension 2 strata, which is this coincidence strata. And then we have non-trivial strata, which again, they come into 2 families, the single jet type, where we have the swallowtail, and the multi-jet type, where we have big and the triple point. And that's what the codimension 2 strata look like. The next thing that we need to understand is, well, I told you about the codimension 2 strata, but there is something more that needs to be said in order to cover all possible 2-parameter Cerf paths, which I haven't said yet. But do you want me to say it now, or shall we take a break? Let's take a break, I agree. So we're going to take a 10-minute break, and then we'll come back for the rest.
Thanks, Filippos.
Okay, we're back. I hope, can you hear?
Yes, I can hear.
Perfect, okay. All right, so we talked about co-dimension 2 strata, the space of smooth real life functions. I now want to talk about two-parameter surf paths. You might think that I've already told you what these things are, and I've told you to a great extent, but not everything, because there's always room for more complexity. So the thing is that when we defined surf paths, there was basically two things that we had to worry about. One thing was what the co-dimension 1 strata looked like. But then we didn't just say that surf paths are paths in F0 union F1. We excluded a bunch of paths that generically wouldn't appear. And to rephrase that, we didn't just want to cross the co-dimension 1 strata, but we wanted to cross them in a genuine way. We didn't want to cross them in what I'm calling here a fake way. So this is an example of something that we excluded as a surf path. It's a surf path, so it's a path functions. So here again, this is my f of w, and here I have this path of functions. This orange line is a cusp co-dimension 1 stratum, and here I'm going from the right to the left, so I guess I'm attempting to go from the right to the left. That if I want to cross this genuinely, I would have a birth. Here I'm having something that I'm calling a fake birth. Exactly, yeah, I did, exactly. And this is, this is one of the things that we excluded when we were talking about surf paths, because if you give me something like that where I didn't have the courage to cross, I can always just perturb it a little bit into a path like that, into a path like that, where I cross. Okay, so I can always, at the one parameter case, I can just perturb a little bit so this phenomenon doesn't occur. But if I want to describe a homotopy, so if I wanted to describe, say, a homotopy between this little path and this bigger path, then I wouldn't be able to avoid those. So these are all the extra ones that I need to add in order to have a complete description of the two-parameter surf paths. Like here, I'm not introducing any new strata. I'm just relaxing this condition about how we cross this strata. This is where this new two-parameter paths show up. Precisely, yeah. So what you have, yeah, I'll draw all the cases that show up. So here I said this is a fake birth. Let me make the easiest case where this is 0 and 2. And so the left-hand side, I have to be gamma 0 and this gamma 1. My surf graphic that be empty. My surf graphic for that would be something of this sort. I would have a birth here, and then I would have death. Okay, well, I guess, sorry. I was meant to write this. I was meant to write this here, and I was meant to just write a point here. That's the intermediate. So that's so this move I'm just calling this path here fake birth, and then the move surf graphic sometimes is called the eye, because you have like eye appearing. Some people might call that leaps. I don't know. Likewise, we have a fake depth. If I do that, if I do this on the other side, I may have a fake depth where again the surf graphic for the depth would be two fold lines, and then after the depth, sorry, after the fake depth, I would actually have death and birth. It would be like that. And there is an intermediate stage where it would look like, oops.
As in you never actually cross F2, but still you need to.
Exactly. And similarly, and so this is sometimes called the merge unmerge move.
And the abstractions here?
Yeah, there are. So, but the abstractions here is basically, so you have two critical points, P0, P1, and I should be able to kill them. So it's the same abstraction that we would have for the clasp. And then we have the fake crossing, which is a similar situation where I would have two fold lines, and then I would cross them once, and then I would cross them again. And the intermediate would be something like this, which might look like a crossing. It's not. It's a fake crossing. This is like C0, C0, C1, C1. Okay. And so my stratification tree for the two-parameter surf paths, it's basically my stratification tree for the F2 strata plus these fake surf paths that have that, fake births, fake deaths, and fake crossings. Okay, and that gives me the description of what the two-parameter surf paths look like. I mean, I didn't precisely define them for you, but at least I told you what locally they look like. Okay. So, are there any questions, concerns? Because we're going to change page now a little bit.
So, I would like to, since in my head, surf is very big and scary paper, just if you would just point out what you've said, maybe that is surf. Or
yeah.
Just let's get a surf.
So what I'm going to do, because I was planning to do, is I'm going to point where some of that is being used. So now, I've basically almost given you like most of the technical things that are required, modulo some things that I haven't actually proved. And now I want to use in the way you sort of use them to get proof of the pseudo-isotopy theory. So I'll definitely point where some of the things that we've introduced are used by SERP. But no. But he does do it. I mean, he does do it quite systematically. So if you want to get like an overview of where these things would be in SERP, you would read the introduction. So in the introduction, he actually does a good job of like outlining like the F0, the F1, the F2. And then you have to look into individual chapters to get more details about.
You said the Surf in 1970 French.
Yeah, he wrote a lot. That's the last certification. I can't speak French, but yeah, that one. Natural certification of, yeah, that 170-page book, it's the last paper, yeah.
Maybe
Hi, Ken. Can you give us a nice pronunciation of the natural certification paper?
In French, is there a translation?
Now, yes.
Okay.
With some good translate. So now I just want to like get us started with thinking about how to use everything we introduced to simplify surf graphics. Okay, and the first thing, like the first step towards a simple. Oh, and also, sorry, before doing that, an answer to you, Bruce. There's a surf paper, but there's also John Morgan's lecture videos and some lecture notes. So I wrote that in the title, and those are great help to get into that. So today I'm actually following to a certain extent John Morgan as well. So ordering the critical points, that's going to be the first step in simplifying surf graphics. And the first thing to say is, well, before we go into surf graphics and surf paths, if you just give me excellent Morse function, what does it mean for it to be ordered? It means that if I have any two critical points, such that one is higher than the other, then the index of the higher critical point must be greater than or equal to the index of the lower critical point. So it's this condition. If C0 and C1 are my two critical points, and f of C0 is greater than f of C1, then I must have that the index of C0 is greater than or equal to the index of C1. And that's what it means for an excellent function to be ordered. And then a surf path will be ordered if at all quote-unquote excellent Morse time, what we would have is an ordered excellent Morse function. And this is quite a strong condition. I mean, for example, you know, if my surf path has a crossing and I have C0 and C1, the only way I can have crossing my surf path is ordered is if the index of C0 equals the index of C1. Otherwise, I wouldn't be able to.
What is the index?
So if you remember how when we defined the Morse critical points, so we said a Morse critical point has a specific local behavior. So it looks like minus x1 squared blah, 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 minus xi squared plus xi plus 1 squared plus 1 squared. So I is the index. Okay, and yeah, so just saying, if you have a surf graphic that is ordered and you have a crossing, then that gives you a condition for what the indices must be here. And likewise, if you have, say, a death or a birth, and this is C0, C1, I might have some other critical points above C1 and below C0, and I must know that, well, actually, this isn't saying anything profound. This is just repeating what it means to be an ordered Morse function. But maybe I should say that if I have a birth, I can only do, so if I have a birth, I give rise to C0 and C1, and I must have that the index of the critical point that I'm giving rise to be greater than or equal to all the critical points below it. And likewise, the other one, C1, must have index, which is less than or equal to all the critical points above it. So again, it's like precise condition. And I should, the index here is I. Its index will be I plus 1. So I know that all of these must be less than or equal to I. And all of these must be greater or equal to I plus 1.
You just move it slightly up so you can see what it's saying?
Yeah, the theorem, I didn't get the theorem. The theorem says that there always exists an ordered surf-path that connects two functions with no critical points. So this is going to be our first step towards simplification of the paths that occur between two functions without critical points. Remember that our eventual goal is to get to a place where if you give me two functions with no critical points under some conditions of the underlying manifold, I can connect them path a function without critical points. And I'm trying to like get us into a program that will get to this result. And so the first step is this theory. Don't seem happy.
Sure. I'll last back with the big picture. If you just go up to where we're describing it in the first 5 minutes again, we're making connections to the isotopic problem.
Yes.
So, this is important.
Yeah, no, it's important for sure.
Okay.
So this is what we want to prove. Right? We want to prove that if you give me two functions without critical points, the question is, can I always find a path between them that is a path of smooth functions without critical points? And that's the equivalent question as to if you give me any path of smooth functions between them, can I homotopy its relative endpoints to a path without critical points? And what I'm saying is that so basically what I want to do is that I want to start with a path of smooth functions, and I want to simplify it as much as possible. Eventually, I want to simplify it enough so that I get into a path without critical points. The first step of the simplification process will be that I'm going to homotopy relative endpoints to a path that is ordered, a surf path that is ordered. So I guess I already know, I've already shown to you that any such path is homotopic relative endpoints to a surf path. That's the genericity of surf paths. And now I'm going to take any surf path and I'm going to homotopy to an ordered surf path.
I'll go back to where we are now because it doesn't seem to be exactly the same.
Yeah, it's not exactly a statement. I'm claiming that's an equivalent statement. Sorry, where was that? Yeah, maybe I should have stated it as any surf path between functions with no critical points. It's homotopic relative endpoints to a surf path, to an ordered surf path.
But I guess in order to make that statement, we first of all have to, because an ordered surf path has to go between ordered functions at the end, right? You can't talk about ordered. The ordered surf path is ordered Morse function on the one side, ordered Morse function on the other side, and as you go from one to the other,
Exactly.
Right, so,
But the two Morse functions on the side have no critical points, so they are ordered.
So in other words, what we're doing is inside those orange blocks in your picture, we're moving those dots around, so getting an endpoints around in those orange blocks, starting with.
Well, we do, but we don't have to though, because any function without critical points is ordered.
Yeah.
So this doesn't affect us. Everything in the orange box is ordered because it has no critical point.
Okay. Yeah. This is weird. I just don't. Okay. So, okay. I don't see how to make a connection between this theorem and the idea of trying to simplify a given. We've got a surf path between our two functions.
Right.
We're trying to simplify.
Yeah.
How is this theorem to assist us?
Well, first we're going to turn it into a path that is ordered, and then we're going to have, well, that was meant to be like next week. Then if you give me an ordered path, I can make some moves to it that will take away lots of critical points.
How is this theorem going to help us to change our path to an ordered path?
When you say this theorem, sorry, this theorem, I mean, think of this statement as I should not have written the statement like that. The statement that I want is that any surf path is homotopic to an ordered one if the endpoints have no critical. So
endpoints is no critical points at endpoint.
No.
We've got a path to ordered. It's not necessarily ordered. We're going to have a subject.
that's what the theorem is. Exactly. And I have some preliminary things to say. Unfortunately, we're not done with all the preliminary things before the plan begins, but some geometric condition that for when crossing some clasps occur. So this goes. Okay, good. I'm not spending too much time on the good stuff, but the goal here, yes, again, to apply motion surf graphics. And there's the question that Bruce has already asked, like what conditions are necessary in order to apply the surf moves that we've seen. And so I guess some preliminary definitions, if you give me a manifold M, choose a Riemannian metric on it, and choose an excellent Morse function. So I'm going to denote by phi sub t this family of diffeomorphisms that I'm going to get, which are induced by the gradient flow of f, and it's basically it's like flowing for time t. That's what this diffeomorphism is, using the gradient flow to flow for time t. That gives me this family of diffeomorphisms. And if you start with a critical point P, there's two manifolds which are quite important for us. There's the ascending and descending manifold. So this is the definition, and this is the picture to keep in mind. If this is the pair of copans with the height function, critical point P, the ascending manifold of P consists of all those points in X that eventually will flow back to P. So this is what this green part looks like. Likewise, the descending manifold of P is all of these points in X that eventually will flow to P. So this is what the orange, I think, looks like. Likewise, if my surface is just this disk with a height function and I have my critical point P, here the descending manifold is the entire disk. All the points are going to flow to P. And what I'm using as a claim, and I'll be using as a claim, is that the ascending manifold of P is diffeomorphic to an open disk of dimension n minus the index of P, and the descending manifold of P is diffeomorphic to an open disk of dimension the index of P. Okay? So I don't strictly need this definition, but I'm going to give it for completeness. A pair f comma g, so f is an excellent Morse function and g is a Riemannian metric. Pair like that will be called Morse-Male if f is excellent Morse, and for every pair of critical points P and Q, the ascending manifold of sorry, the ascending manifold of P and the descending manifold of Q intersect transversely. And there's again the claim that if you look at the space of smooth real value functions across the space of real metrics, these pairs, the Morse pairs, are actually generic. And now I guess I can actually state what sort of geometric conditions are to have cancellation of crossing for two critical points to be in cancelling position. What I would like to have is that I would like to have some level set L where the boundary of the descending manifold, the boundary of the descending manifold I guess what I want is, I want the descending disk of P and the ascending disk of Q to intersect transversally at a single point at level L. That's the condition. So here I have 2 points P and Q. They are in cancelling position. This is their disk. The orange disk is the descending disk of P, and the green disk is the ascending disk of Q, and they intersect at a single point at the level set.
Just go up, and then we put maybe possibly or exactly you go up to when you talk about Morse-Cerf.
Yeah.
It seems to me like didn't you say that the ascending disk, intersects in the level set because they, like in our picture, they're not intersecting transversely in M.
Yeah.
Shouldn't you add that as a proviso here?
Where?
In the definition, because otherwise this our Morse function. This would be more small. Like the yellow manifold is not affecting green manifold transversely, but only in the level set L.
Well, I mean, first of all, I'm not claiming that this is Morse-Cerf. So this is like an independent thing. But I'm not sure if.
Yeah, I think I'm wrong.
I think this is fine.
So a little bit confusing.
Yeah. And then for, I guess, 2 critical points to be in a crossing position, P and Q, if they are consecutive, so there's no critical points between P and Q, and say f of P is greater than f of Q, then the condition is that the descending disk of P extends below the level of FQ without ever crossing Q. So that's the exactly. And this one has a nice also curl, which is that you give me critical points in Q which are consecutive, and f of P is greater than f of Q. So just like the picture here, if it so happens that the index of P is less than the index of Q, then there is going to be a crossing starting at F that interchanges P and Q and doesn't affect other critical points. So this is, I gave myself space to write the proof and didn't write the proof, which maybe wasn't the best idea. But I think, let's see. So we have a situation where we have a Morse graphic like this, and I have f of P here, f of Q here. I know that the index of P is less than the index of Q. That implies that n minus the index of Q is less than n minus the index of P. and I have that the dimension of the descending disk P is equal to the index of P. Sorry, that's descending. And the dimension of the ascending disk of Q is n minus index of Q. So that thing is index of P plus n minus index of Q. And that is going to be less than n. So I have two submanifolds whose the sum of their dimensions is less than the ambient dimension of the manifold. So generically, they're not going to intersect. And yeah, so if you just give me f, I can perturb f a little bit to make it more small, and then I would know that precisely because of this condition, I cannot have non-trivial transversal intersection between the corresponding ascending and descending disks. And so that would conclude that the ascending disk of P can extend below the descending disk of Q. So it can extend below Q, and therefore I can have a crossing. Essentially like a special. Is that clear? Or?
The only thing which I think running the water is when you said we know that we don't have a transversal crossing.
Yeah.
But in these dimensions, that means that actually they don't cross at all.
Yeah.
Right. Because the the condition is that you don't want to cross at all.
Right.
And that's what we've just been guaranteed from the transversality theorem. It's one of it's that vacuous part.
Exactly. That's the vacuous part of transversality. But you have to say, I mean, they could have crossed transversally.
I see.
But if you are more small, so you need to like impose the transversality condition and then use it. That's all I say. Okay. Let's see. Are we? So this is. I think this ends the preliminary. All the preliminary sections. So now we can actually use stuff to like prove things. But are we feeling strong to go into? Yeah. Okay.
I have a question. I'm sorry.
Please. No.
Until I say when. Just earlier, you drew a diagram, right? A diagram where you had two critical points, and you said the index of the pair is less than the index of the.
I think this one. Yeah.
How do you know the below or less, and the is above or greater?
Right, because I'm just making the assumption that the Cerf path is ordered.
Okay.
So I'm saying under this assumption, the only way this can happen, and I have a birth, is if I have this.
Okay. Yeah, because I agree with you that whenever you have a birth, this will be plus minus 1. And likewise at a death point. But in general, they need not be all.
Definitely not.
Right.
Yeah.
No, happy.
Okay.
Okay.
Okay. Are we?
I'm trying to.
Disappointed.
Disappointment with the. Yeah, anyway, maybe one page battle.
Yeah. See, I don't think it's worth doing only one page. I think. Huh?
Okay, I agree. Okay.
It's always the recording.
Yeah.
Okay. Okay. Now, I'm going to go into like the proof strategy for like ordering theorem. Okay, first some definitions, but a pair of critical points for an excellent Morse function is going to be in that position if I am in this situation where one of the critical points is above the other, that doesn't reflect what's happening with the indices. So yeah, exactly. So I'm going to call that the bad position, and I'm gonna define pad of f. I started learning programming very recently, so I'm a little bit affected in how I define functions. But so I'm going to just define pad of f to be the number of like unordered pairs of critical points that are in bad position. Okay, and I'm going to define a stratification of F0W. So F0W is the space of excellent Morse functions. I'm going to stratify that. Okay, I'm going to stratify it via these spaces F0 sub n. What's F0 sub n of W? Consists of all those excellent Morse functions whose number of pairs of critical points in bad position is less than or equal to n. Okay, so for example, F0W is exactly the old excellent Morse function. Similarly, I could get a stratification of FW. It's a different stratification of the one we've been talking about in the rest of the course. And it's a stratification via these F sub n of W. So these are like all functions such that if I take a neighborhood of them and intersect it with a space of excellent Morse functions, that's going to leave in F0 n. And I get to define F1 of W to be the intersection of, so F1 sub n of W to be the intersection of F1 W with this, and likewise I can take F1 of F1 sub n and union F0 sub n, and I'm going with F tilde 1 sub n. Okay, do you? Yeah. I'm just gonna give you a lemma that we are going to reduce this ordering theorem to. And the lemma is as follows. If you give me f and g to be in f0 n of w, so these are excellent Morse functions that have at most n pairs of critical points in bad position. And you give me a path gamma, which is a surf path from F to G, and it's completely contained in F1 tilde n plus 1. This means that this is a surf path, such that at each point I have excellent Morse functions with at most n plus 1 critical pairs of critical points in bad position.
Wait, they're not excellent.
I'm just taking the excellent Morse time. So this is, yeah, the way I've defined these things here. I mean, it's a convoluted notation to basically just indicate that if you want to look at like what the bad index of function with the CAS base, just look to the left of the lines.
Great notation.
Okay. And what the lemma says, so if I am, so do you understand what the situation is? The situation clearly. So if I am in this situation, then gamma is homotopic real boundary to a surf path from F to G that is completely contained within F sub n.
Also, reducing the badness.
Exactly, I'm reducing the balance of the path. That's what the lemma says. And I actually prove that this lemma implies the theorem, or is it clear that this lemma implies the theorem? Yeah.
I think it's very, you just reduce the values of the path of one, so you keep doing it, right?
Yeah, that's basically. But so that is okay. You don't, you see?
Yeah.
Yeah.
literally just apply it again.
I mean, the idea is like if you are right, like we are in a situation where f and g are f0, 0, but f0, 0 is like f0n for nn. So it's basically, if you give me any surf path, the surf path is going to live inside f1n for some n, and then reiterating. Yeah?
Yeah.
You don't want to write it down.
If you slot an f0, 0, like f0n.
Yeah.
Oh, okay.
Exactly. Then we can apply this lemma.
Yeah.
And the only thing that we need to know is that, like, for a given surf path, there exists n such that this surf path lies in f1 tilde sub n. But that's true because, I mean, our manifolds are compact, and therefore the number of critical points is finite. So,
At most n.
exactly.
Why do you
So
say first?
If they were completely unordered.
Oh, okay. Good point.
okay, so are we happy with, you don't want me to write it down. Okay, now, if we're still strong, I can give you a glimpse of the proof of the lemma. I can give you an overview of that. It's a really elegant argument. So it goes like this. Let's suppose that we are given an excellent Morse function that, like, its badness is n, and I have surf path that crosses f1 once, and let's say it connects f with f prime. So this is, I think this is the picture.
Interesting.
Yeah. So this is the picture that I want to sort of like have in our heads. We have two functions, f and g, and those functions are f sub n of w. I have badness n, and I have a path, and all functions within this path have badness of n plus 1. The other thing that I'm indicating in this picture is these blue points. So this is a surf path. As a surf path, it means that there are finitely many times when you cross an F1 stratum. This is what these blue points indicate those times where I have a Casper crossing. Exactly, yeah.
What is pink line?
That's the stratification between the badnesses.
Oh, that's the badness.
That's the badness. Exactly. And
Okay, so that blue line and the pink line will coincide.
yeah, it is because so in order to go from f sub n to f sub n plus 1, it means that you must have done something the surf path, like can't just, you need to either have a crossing or a bird breadth. Like otherwise you don't change the relative positions of the critical points. So there's, so you cannot cross the pink line without the blue line to do that. And then there will be, and I should say there's like, you know, the like a general path indicated by this lemma might look like that, like you can cross again, but I just, you know, I'm going to concentrate into like one piece at a time. If I tell you how to deal with all situations like this, then I've told you how to deal with like all the ways I can concatenate those together. Is that clear? And So this is step one. What I just said is that I break my surf path into pieces that look like the one above. So general path as the one indicated by the lemma might be a concatenation of these things. That's fine. And the blue marks indicate points where the surf path crosses F1. Okay. Now, step two is show that my surf path is homotopic roll boundary to a surf path that can be decomposed into pieces of this form. So I wanna deal with only paths where once I crossed the pink barrier, I only have one codimensional stratum. At most. You can also say. Okay. So I basically want to go. I basically want to take this guy, and exactly. So I want to take this guy, and I want to top it into something that looks like concatenation of these guys. Okay. So I'm going to tell you how to do that. It's an elegant argument. That's the proof of step two. And I'm going to start with this guy that we have, and look at this little piece that I have with orange. Okay, what is this? If I just look at the orange part, I have a path of Morse functions, and I don't cross the F1 strata while I am in this orange part. What does that mean? It means that my surf graphic looks like this. Okay, I don't cross anything. I don't have any birth deaths. And so my surf, so this path, the orange path, lies completely within F0 sub n plus 1 bubbles. Okay, is that clear? Now, n is greater than or equal to 0, so n plus 1 is greater than or equal to 1. So in particular, we know that there will be at least one bad pair of points in this orange bit. And if there is at least one bad pair of points, there must be at least one consecutive bad pair of points. So I can have, I would necessarily have at some point two critical points that are consecutive, and f of p will be greater than f of q, and the index of p will be less than the index of q. Is that clear? What is happening? It's like there's no way I can like look at all your bad pairs of points. They're like
most least bad thing.
Yeah, there's like necessarily you will have one that pair where there won't be any other critical points in between. Otherwise I would be able to another. Yeah, okay. So I'm calling those P and Q, and I'm writing them like that. So what's happening here? I have the critical point P and I have the critical point Q with f of P greater than or equal to greater than f of Q. And the index of P is less than the index of Q. So I'm in this situation. Remember this small technical preliminary thing that I told you. If I have two critical points P and Q and I have f of P is bigger than f of Q and they're consecutive, but the index of P is less than the index of Q, I can have a crossing path. That's the thing that we're discussing. So since I can have a crossing path, that means that I can do this Riemann-Master 2. So I can apply my surf graphic move that tells me that the surf graphic on the right is the same as the surf graphic on the left. Okay. Now let's look at the surf graphic on the right. The surf graphic on the right, we have this thing where we have Q and P, and those are in bad position. I cross them like that. So here they are in good position. So when I do this crossing, I am reducing the badness by 1. And then here again, I am increasing No, it's by 1. Okay. And here I'm again increasing the badness. So what does that look like in the big picture that I drew?
Considering the left piece. Yeah.
Exactly. And then I carry on with the other ones.
Crocheting.
Crocheting it, exactly. And this exact argument, so I basically have things of 3 types to worry about. One thing is it has this form. It's I have a cross when I am going to n plus 1. Here I will have either a cross or a cusp that is neutral, it doesn't change the badness. Here I would have a cross again. Or I might have this configuration where here I've had a birth, and then here I have a cross and nothing in between. And here I have a cross and here I have a death and nothing in between. So the idea is, in this argument, if this was a cross and this was a cross, do nothing. If this was a birth, this cannot be a death because a death can never increase badness. Only a birth can increase badness. If this was a birth, then I would apply the same argument that I did with this orange part. And I would, and I would bring that one down. Fair. Correct. So that's what the general situation looks like. Okay, and I'm just saying, if this here happened to be a birth, apply the same argument so that I get into this situation. And if it was a cross, do nothing. It can't be a death because death cannot increase badness. And likewise here, if this was a death, apply this same argument in this arc to end in this situation. It can't be a birth because a birth cannot decrease badness. And if it's a cross, do nothing. So there's basically, there's 3 cases, right? There's the case of cross, and anything here that is neutral, birth cross, and cross death. And now it's basically just enumerate everything that could possibly happen in those cases and deal with them. So if you have, if you have a birth cross, what can happen with a birth cross? You might have birth that increases badness by plus, and a cross that decreases badness by 1. And so this is like one possible configuration that might be occurring. Then if we use coincidence, I can bring the crossing first, the cusp afterwards, and so I can move this guy down. This is exactly. Well, I mean, no, this is, I'm just giving an example here. And so this is the example where those things are disjunct from each other. So I can use it. And I just wanted to give you like a glimpse, so I didn't include like all the possibilities. But the way the argument goes is then by just checking all the possibilities. So I wanted to do that maybe in detail next time, or if you're happy, we can do something else next time. But it's a full argument.
Is there anything that uses swallowtail?
Right. So we're not using the swallowtail here. The swallowtail will be, once we have an ordered graphic, we're then going to go into the second step of the simplification, where you give me an ordered graphic, and I end up with a graphic in the end that only has critical points of two indices, I and I plus 1, and nothing else. And that's the second step in the simplification process, and that gives the swap test.
Because I would like to be assured that at each, whenever we do these simplifications, that at each stage we are assured that there's no obstructions. That's all.
Definitely, yeah. So the plan, so next time should be relatively fun. It should be, I mean, it was meant to be this time as well, but it's basically checking all the possibilities and like playing with those moves and seeing that things simplify the way you want to simplify. So I went 10 minutes of time.
Is that second to last?
Yeah, so next week, not tomorrow, but next Wednesday.
Okay.
Yeah, because I was.
Yeah. And then so, I mean, it's like we're gonna quite get high one calculation that we're going to.
Well, but we are going to go up to the last step.
Because we're making some headway.
Yeah.
We're still missing.
So I mean, what we want in order to like calculate the, I mean, we want to prove that this Python is trivial. So we want to prove that I completely simplify my subgraph. I won't be able to completely simplify the subgraphics, but I'll be able to simplify them quite a bit. So there, to order, then the next step would be to get them to only have two kinds of critical points. So critical points of indices I and I plus 1 only for some I and nothing else. And then there is a last step, which is you give me a surf graphic with only two kinds of critical points like that. You can eliminate them. That is something that actually requires algebraic theory. So that's like the last chapter of surf. And
That's the only whole thing I mean.
yeah.
You're going to take as far as you can do general dimensions.
I have to double. I think the ordering. I think the ordering is for general dimensions. Might be that even next time we're going into.
But elimination is like pairwise elimination.
Yeah.
Because they differ by.
Yeah.
So saying that we can find kill them in pairs.
Yeah. But I don't. So it's part of the argument. I don't actually fully know myself very well. So I know that it's a part of the argument that makes the bridge to algebraic K-theory, so it's where the algebraic K-theory shows up, but I haven't gone through it in detail myself. So I'll get you up to where algebraic K-theory can give you the rest. That's sorry?
Yeah. Okay. Cheers,